Okay, in this one, we've got a bullet shot into a tree, and I want the impulse delivered to the bullet by the tree. Our impulse, by definition, is force times the time interval during which the force was acting, and we know neither the force nor the time interval, so we're probably not going to be able to get the impulse directly from the definition. However, the impulse-momentum relationship states that the impulse is equal to the change in momentum. Alright, here we've got enough information to calculate the change in momentum. Momentum, P is just mv, and we've got the mass and the velocity in the before picture, and it comes to rest, so the momentum in the after picture is 0. So we can use this J is equal to delta P idea, the impulse-momentum relationship, in order to calculate the impulse. I call it coming in the back door where the front door would be using the definition. Alright, let's get a before and after picture. We'll have before. We'll have a bullet traveling along at velocity v equals 220 meters per second with mass m equal 0.040 kilograms, and it's headed for a tree. In the after picture, we have the tree with the bullet stuck in it. I think I'll call that V2 for the bullet being equal to 0, and I'm going to call this V1. Our momentum change, delta P, is the final minus the initial. I'm going to use, instead of the full vector notation, I'll call the positive direction to the right, and all momenta to the right will thus be positive, and the impulse, the direction will be characterized by a plus or minus sign for our resultant impulse. And we've got 0. The object is at rest in the after picture. V2 is equal to 0, so the momentum is equal to 0 by inspection. Or you could use 0.040 kilograms times 0 is 0. But at any rate, P2 is 0. And I'll look at this as minus V1. So J is equal to minus M1 V1, which is minus the, and it's not M1 V1, just MV1, the mass of the bullet. And that's equal to minus 0.040 kilograms, good to 2 sig figs, times 220 meters per second, good to 2 or 3 sig figs. We've got an ambiguous situation here, whole number ending in a 0. So J, in our convention, is just minus 8.8 kilogram meters seconds, which is equivalent to a Newton second. I think I'll prove that going the opposite way. A Newton is a kilogram meter per second squared, and if we multiply that times a second, so a Newton second, seconds cancel. A Newton second is the same thing as a kilogram meter per second. Just working out the units as an aside. Alright. We'll interpret the minus sign there. The impulse for the reader is 8.8 Newton seconds in the direction opposite that of the initial or pre-collision velocity of the bullet. And I think I do like that word pre-collision better. I'll put a little hyphen in there. The pre-collision velocity of the bullet, and that's the answer for SAC 125.